Welcome to ICDD's InSession webinars and Dr. Anja Dosen's presentation, ICDD Grant-in-Aid, Data Submission Process and Quality Standards.
Today we're going to be talking about Grant-in-Aid program and a little bit about the data submission process, and I'm going to be focusing on the data quality standards for the data that we publish in the Powder Diffraction File. So the Grant-in-Aid program is a program that the ICDD has for many years, and the Grant-in-Aid program provides funds and grants to researchers around the world for high quality X-ray diffraction data. So this program is international. As a member of a Grant-in-Aid program or as a grantee, you have several benefits like a discounted product, PDF 5 Plus, financial support for your lab and research, publication of your patterns in the Powder Diffraction database, and 1 year complimentary subscription to our Powder Diffraction journal. So as I said, our Grant-in-Aid program is international. ICDD is an international organization. We have grantees from all over the world. Like you can see this map, all the countries that are dark blue. That's where we have or had grantees in the past. So anyone is welcome to apply for the Grant-in-Aid program, and we can evaluate your proposal and see if we can include your data in the Powder Diffraction database. Over the last 15 years, the Grant-in-Aid has awarded more than $4 million, and we've funded, now this number is over 500, we've funded over 500 proposals. We have 2 deadlines per year for a Grant-in-Aid process. One is in January, coming up this January 31st. So if anyone is eager, you can still make this deadline. And then the next deadline is July 31st for your proposals for Grant-in-Aid. A great thing about the funds that we provide is that they come with no strings attached, so they're not dedicated funds for a certain thing in your lab or in your research. You're free to use the funds in any way you think is the most beneficial for you. For example, lab equipment, research supplies. You can use it for financial support for someone in your research group and so on. So funds are available for you to use it as you think best. So I've mentioned this briefly. I'll mention some of these benefits again. Your data will be published, included in the PDF diffraction file. You will be awarded a certificate of publication. You have a discount on the ICDD product and a complimentary subscription to Powder Diffraction Journal for 1 year. So the best thing I want to say, in my opinion, is the benefit that you have 50% off the PDF 5 Plus product. So PDF 5 Plus product is our most comprehensive database. It includes organic entries, inorganic, pharmaceuticals, minerals, everything really that we have, all data is included in the PDF 5 Plus database. It has over 1 million entries. It contains entries with raw data. It contains entries with atomic coordinates. And so it also, recently we've incorporated Raman data. So that is included in this database as well. I mentioned atomic coordinates for structure-based studies and modeling, and all supporting tools that are included in this database. So as a grantee, you have access to this comprehensive database at half the cost. What is required? So, as you know, PDF database is a reference database for powder diffraction standards. So from our grantees, we require high quality data. So high quality X-ray diffraction patterns that are well characterized chemically and crystallographically with supporting data, analytical data like chemical analysis, XRF, TGA, whatever is the best method for characterizing your materials. All peaks need to be indexed. You know, when you use our database, the peaks, we have a peak list, intensity and peak position list. So all significant peaks must be indexed. Any unindexed peaks, for whatever reason, if there must be an unindexed peak, it needs to be clearly explained why that peak is unindexed. Pattern should be high precision, as we say, preferably delta 2 theta less than 0.03 degrees, and that will be determined using an internal standard reference material, which I will be talking about in a little bit. Entries are prepared using our in-house software that's called Data Quacker. We'll have a little video later on showing how this process is done. What we require both integrated intensities and peak intensities, just intensities and peak positions. And submissions should include sample preparation, physical properties, and compound classifications. For organic patterns, we require a 2D structural diagram showing the organic structure. And there are CAS register numbers. They're required as well. So we're going to talk a little bit about collecting diffraction data now and what are some of the most important things to obtain a high quality diffraction pattern. So we're going to start talking about sample preparation, and careful sample preparation is the most important step, or one of the most important steps. So regardless of what your material is, it is important to pay attention to have uniform particle size, to have a representative sample. You need to pay attention to correct sample loading in the sample holder and avoiding preferred orientation if there is any in your sample. The next thing that we're going to talk about is instrumental setup and alignment. So we're talking about like sample displacement and zero shift and the appropriate instrumental setup. And then data collection parameters, which is these three, all of these steps are equally important, but I guess like sample preparation is the first, and that's why we say most important steps. So data collection parameters are also important. What you need to have a representative scan range, good count time and step size, and correct radiation choice for your particular samples. So let's talk about the sample preparation and standard reference material now. What we say when we say ensure representative sampling, your sample should represent should represent well the bulk material. This is very, very important when we're talking about multi-phase samples, but in our case, for the PDF database, we need to obtain a single phase sample. So in this case, when we say represent the bulk material, is avoid segregation by particle size or by density, have a homogeneous particle size. Sample should be mixed thoroughly to be homogenized and as representative as possible. So then particle size should be also homogenized. You can use grinding. Generally, we would like to see a fine powder, typically less than 10 or 20 microns. This in turn improves the peak statistics, and you should. Good tip is to pay attention to avoid phase change or contamination, and then which means like fine and gentle grinding, something that is not going to influence or change your sample. And if your sample is very susceptible to shearing or phase transitions, you could consider wet grinding that reduces the temperature and homogenizes the sample. What is the goal? The goal is to achieve random crystallite size orientation. We don't want to see any preferred orientation because that will show us it will show us some peaks that are going to be preferentially oriented, and sometimes depending on the sample we may not see all HKL reflection. So platy or needle-like phases need special care to avoid preferred orientation. Sample holder choice is also an important thing. Appropriate sample holder, we want to use a flat plate holder for routine analysis. If you have a very small amount of sample, zero background holders are a good idea. And if you have enough sample, backs or side loading sample holders are preferable, and also these sample holders allow you to load the sample in a way to avoid preferred orientation, usually using like a rough surface that would not that won't leave your sample surface completely smooth if there is preferred orientation that you want to avoid. On the other hand, you do want to have like an even surface when you're filling out your sample holder. So here's an example. This is an example of alpha aluminum or corundum. The top image here is the sample that was prepared in-house, and the bottom image is the sample that is this is a Brooker solid corundum sample. So this is the standard sample, internal standard that Brooker offers. All vendors will offer some usually corundum as an internal standard for instrumental alignment. So this this process that I'm going to show now is process that shows you how well your instrument is aligned. Okay, so as you see, I'm just going to go back here for a second. As you see, this this sample here has a very smooth surface, very little grooves here. So if you can imagine, you can see on this flat plate here, this is where the X-ray beam lands. As you can see, a little bit a different color. So you know that the X-ray beam is going to land around here, and this is where you want to have your flat surface, which we have here. So what this slide shows is the peak comparison between the standard, internal standard, and the sample that was analyzed in-house. And as you can see, in this case, black is the same in-house sample and red is the internal standard. As you can see, there is no difference in the peak position. There is a little bit of a difference in peak intensity, but no difference in peak positions, which is very important. And it shows that the instrument has been properly aligned. This is something that we require that you send us as a grantee. Your internal standard so that we can compare it and make sure that your instrument is properly aligned. So sample analysis and instrumental setup. This is the next step we're going to be talking about. So what this slide here shows is that even though we're looking at the more or less same material, as you can see, there is a little bit of like a slight difference between the chromium and iron content in these samples. We see a fairly different diffraction pattern, and we see that there is a difference in the background noise and the peak sharpness. So let's talk about how the instrumental setup and analysis influences the resulting diffraction patterns. counting statistics is something that is that is always good to consider or necessary to consider. High counts lead to low relative error. Low counts lead to high relative error. So that's something that you should always keep in mind. So if we count, and that is how long your X-ray beam is counting in one position, is hovering in one position. If we count n photons, we have a standard deviation of sigma that is square root of n. So the higher the count we have, the lower the uncertainty we have. Because if we have 10,000 counts, we are going to end up with 1% uncertainty. If we have 100 counts, if we count very fast, if this is something, then we're going to have a 10% uncertainty. So higher count rates significantly reduce statistical error. And as I said, we need to consider this every time we do our analysis. So as I said, the error is going to be 1% for 10,000 counts and 10% for 100 counts. So that's a very big difference, which means in practice that if we count for more, like 10,000 counts, we have a stable signal, and repeated measurements are going to be more or less the same. They're going to vary a little bit. So these are going to be reproducible. However, if we have 100 counts, the signal is much noisier and the measurements are not necessarily going to be reproducible. There is going to be a great variation in your resulting X-ray diffraction pattern of about 10%. Here's an example. This here is an X-ray diffraction pattern of a multi-phase sample that was analyzed 0.5 second count, and we see that our max counts here are around 3,000. If you take a look at the background, it is fairly noisy. We can see all the peaks, but for example, this peak here and then something here, we don't necessarily know if this is the background noise or the peak itself. So now this is the same diffraction pattern, but where we counted 5 seconds. So now we have 70,000 counts. And as you can see, we have lowered the background noise. It is much less noisy. And all of these little peaks that were hard to see are well defined now. So this allows you for better characterization, better whole pattern fitting, retool analysis, phase determination, and so on. So this is something that should always be considered. Now here is the example, same example, but overlaid. So as you can see, this here, you could have mistaken for 2 peaks. But this is just noise. And then if once you analyze it with higher counting statistics, you can see that this is just 1 peak and this here was noise. Same thing here. This could have been mistaken for a peak, but it is just noise. So more counts improve precision. Weak peaks are less precise than strong peaks with lower counts. So you would like to increase the counts as much as you can. And longer count times are important when you want to see minor phases or poorly crystalline materials. Now, this, of course, depends on your lab setup, on what you can do, how much time you have. So it is good to think of what your samples are like and what you can do to get a better counting statistics. What is the best counting statistics that you can get with the parameters that you can use? Okay, so next thing is sample displacement error. This is a very, very common error. Most often we have a little bit of sample displacement, and we could call this like a human error because sometimes it is just how the sample is prepared, and this leads to some displacement. So what happens is if our sample surface is not in the diffractometer's focusing circle, there will be some displacement in the diffraction pattern. That means the sample is not at the correct height. So it will cause a shift in peak position or in 2 theta position, and generally it's going to affect all the reflections in the same direction. So all the reflections is going to move are going to be like shifted to the left or to the right, to the higher or lower 2 theta. So this is at low 2 theta, a small vertical error translates into a large angular shift. So peaks will move noticeably. At high 2 theta, it will produce a smaller angular change, so the shifts will be reduced. So you can see how not all peaks are going to be shifted the exact same amount. It will vary through towards the higher 2 theta range. This is tricky because it can lead to incorrect lattice parameter calculations. Here is an example what this may look like if you have if you load your sample holder, if you don't have enough sample, if your sample is displaced low, there's a shift towards low 2 theta. If it's perfect, if it's aligned, it will be at the correct 2 theta value. And if it's displaced high, it will go towards higher 2 theta value. And this is an example of a cavity holder that's shown here. So what is this? It's overfilling, poorly leveled surfaces, and incorrect mounting. So this is why I said human error. This is something that can be controlled to, the best of your abilities. Sometimes there will be a little bit of a shift, which is generally acceptable if the shift is very small. Here is another example, what this looks like in the diffraction pattern. If the sample is too, if it's packed too high, it will move towards higher 2 theta. And of course, as you can see, and I'm sure that you know this, if the sample is displaced, you're also going to be losing some intensity. So once we have 0 displacement, the sample is at the correct position and it shows the highest intensity peak. Lower displacement, the sample will move towards lower 2 theta, and we're also going to be losing intensity. So these are the most important things to consider when you're preparing your sample and analyzing your sample. So sample displacement, correct instrumental setup, and counting statistics. Now we're going to talk about the Data Quacker program and the Grant-in-Aid, some of the Grant-in-Aid requirements. So Data Quacker is a software that was created in-house here at ICDD, and what it's meant for you to be able to compile all your data together into one file that's going to be easily readable here in-house. So you can add raw data, crystallographic information, chemical formula, names, comments. I'm going to show you a short video in a bit that's going to describe and show you all the steps how to use and compile all the data in Data Quacker. So once Data Quacker is easily downloadable here. This is once you create your Grant-in-Aid profile, you can get to your dashboard, and there is going to be Data Quacker software for you to download. Once you download it, you can download it and unzip it, of course. The first thing when you open it, it's going to ask you for your grantee ID. You'll say okay, and you're going to see this simple little software. It's easy to use, but there's a lot of steps, so that's why I've created a video for you that I'm going to show you just now. So as you can see, you have the cell parameters, names, formulas. This is your instrumental setup, experimental conditions, and so on, all set up in different tabs, and all easily filled up, or you can import your data. So now I want to show you this short video. It's about 10 minutes that's going to describe how to use Data Quacker for data submission at ICDD. So here I've downloaded Data Quacker. This is the icon. I can open it, and it is going to ask you for your grantee ID. I'm just going to put a mock ID here. You should put your own grantee ID, because that way it's going to pull your data and add the reference. Okay, so this is the Data Quacker window. As I've shown before, we have different tabs here that are displaying different information. So cell parameter tab, for example, if you want to import, if you want to type in your data, if you can say powder data cubic cell, and then you can type in your cell parameters here, standard deviation. So as you can see, it knows that it's a cubic system. It just repeats everything and inputs the angles. You can put your Z, let's say, and then you can choose your space group here, and add everything manually. The next tab is the chemical name. Chemical name is linked to chemical formula. So if you are doing chemical formula importing manually, you can input your formula here, and then, for example, let's say silicon dioxide, you can click here, calculate empirical formula. It's going to show you the empirical formula. You can check the formulas to see if they match. It will show you all the formulas down here. And then once you have your formula, it is very important to input the chemical name. And chemical name is going to be, in this case, silicon dioxide. What is important is that you name all the elements that are in the formula, because that is how our system is going to recognize it. Other than that, you can add the common name of your chemical. There needs to be only one chemical name, but then you can add several common names if there are some, or any other names that you see here on the list. Then we have the tab for your instrument, where you can input your instrument information, experimental conditions, temperature and pressure, chemical properties. This is also where you have the preparation conditions for your sample, chemical properties. If there's something important that you want to input here, you can. Classifications, you want to say what your material is. It's inorganic and I don't know, solar material. You can just click these flags. Reference should be pulled automatically if you have your grant number. And then here is the tab for comments. You can input any comments that you want displayed in the database, and these comments are made for you to describe your material in more detail. And then this tab here are atomic coordinates that you can import. I'm going to show you in a minute how. Okay, and then we have the peak list, DA list 1, which is normally integrated peak list, and DA list 2, which is just a peak height list, and then raw data is going to be your raw data tab. Okay, so I'm going to clear all here, and what I have done, I've prepared different files here. So as you can see, I have data here in the CIF format. So that's what I'm going to do. When you do any kind of refinement, you are usually able to export your data in the CIF format, and our program knows how to read the CIF. So GSAS, Foolproof, Topaz, Jade, all of these programs allow you to export a CIF file. Alternatively, you can create it, but you can export it. Okay, so I have my CIF file here. If I try and drag and drop it here, I can't, But if I move up here, it will say move. I can drag and drop it here. I will let go, and it will show me this is the CIF file. It says Data Quacker. This has been prepared in a Data Quacker, and the original analysis was done in Foolproof. Okay, so it's showing me that the formulas are matching. I'm going to say OK, and I can X out of this, and here we have some importance of the material, description of the material. This is the intermetallic compounds for hydrogen storage. This is going to be a little short description of your material. Now when we move to the cell tab, as you can see, it's been populated already because it was in the CIF. You can make any corrections here if you need to. So what I was saying about names and formulas, this is lanthanum nickel silicon. If we go to names, lanthanum nickel silicon. So that is very important that you match the formula and the name. If we go to instrumentation tab, there's some information here like nickel filter, diffractometer, goniometer radius, and so on. Experimental conditions, here we can see the temperature of preparation was 1273 Kelvin, and we have a description of how the material was prepared. And chemical properties, it's an alloy. Reference is going to be empty because I logged in with my mock grant ID, and there aren't any comments because I haven't copied them, but as I said, you can just add comments, any kind of comment in here. Type it in and click add comment. Okay, so now we need to import the raw data and DI lists. I'm going to go to import, new session, raw data. In my case, my raw data is in MDI format, but you have like all of these different formats that the software can read. Okay, so this here is my raw data. I'm going to open it. It's going to ask me about the starting angle, and here it is. It has automatically been imported. 2 theta, intensity, and then the calculated despacing. I can change this or just add that it's X-ray. It already knows that it's copper radiation. Okay, so now I want to import DI list 1, which is an integrated list, and this list was obtained from whole pattern fitting or Lebel or Rietveld analysis. Okay, so DI list 1 done. Now I get this window. So now I want to import despacing and integrated intensity. I'm going to say x-axis is D, intensity is the y-axis. So now I need to say which columns are these in. So the first column are going to be these numbers. Second column is 2 theta. Third column is intensity, so I can already put number 3 here. Fourth is D, 4, and then H, K, and L are 5, 6, and 7. So what is important is that you remove the text lines. It has to start with the values that you're starting to use. So now when I've removed the text column, I can click these 2 arrows and it will populate the table. So when I click finish, I'm going to click other, but when you do any kind of profile fitting, you should label it here. If it's something different, you can label it here and then add details here. So for example, when we use jade, we can click other and then add a jade whole pattern fitting here. Then again, I get to select the probe and radiation. So we said CUK1. Okay, and here is my DI list. Okay, so now you have the DI list 1. This is the integrated list. You can plot your data to see what it looks like. You can zoom in to see how your data fits. See, this fits really nicely. And then you can move on to inserting the list 2, which is going to be the exact same process. I'm choosing a text file, the list 2. Here it is. I'm going to say I want to import despacing, and in this case, peak. So it's not integrated intensity. This is the peak intensity. So let's count the columns again. 1, 2, 3, 4. Despacing is the 4th column. Peak intensity is the 3rd column. And then H, K, L are 5, 6, and 7. Okay, so here we are. Finish. Remember that it's the copper radiation. Now we can plot both DI lists, and as you can see, one is green, the other one is going to be red. So you have here DI list 1, DI list 2, and intensity data. So if I remove include, I'm going to uncheck this. See, DI list 1 and DI list 2 are matching. Sometimes they are, sometimes they aren't, but this is how the process goes. So what are we missing? We're missing the coordinates. That is the last thing we're missing. So I'm going to do the same thing again. Import atomic coordinates. So I'm going to import the atomic coordinates from a text file, and I'm going to choose this file. So here are the atomic coordinates. Okay, so now what we need to do is insert site label. That's going to be 2 atom 3 x 4 5 6. Occupancy is 7. And there is a U ISO column, which is going to be 8. So, again, we don't want to have the text row first, or the column headers. So I'm going to import this and say finish. Okay, so now we have our atomic coordinates as well. Okay, so now we have everything, and this is your entire process that you need to do. Now you can go to save session. It is going to give you all the comparisons, and it's going to save this as a DFT file. So you can save it as DFT file. Okay, so we didn't select the ADP. Okay, so if there's this is a U ISO, so now we can go and save this again. So you can save it as a DFT file, and you can save it as a CIF file, and those are formats that you can send to us. So this is the process, and now you have a file that is ready to be used. All right, thank you for watching this little video. Now we're going back to our presentation. I'm just going to go through a few more important points regarding the Grant-in-Aid submission. So we talked about the data quality. Now, data quality in proposed phases. What are some requirements? Phases must be new and unpublished. So they should be of high interest for phase ID, something usually grantees that work on current research have phases that are creating phases or synthesizing phases that are of high interest for phase ID. So after all of this is done and you've done all these steps in Data Quacker, you can use Data Quacker Graph to carefully review your diffraction data. All peaks should be correctly labeled, and you need to make sure that you're including all minor and major reflections. So data should be clean and free of impurities. So I'm going to show you in the next slide what happens if the impurities are unavoidable, because there are instances where they are unavoidable. Let's see. So what is important here to see? So what are some acceptable and unacceptable examples? This is a fairly complex material. It has a lot of metals in it, and so it was created by mixing metal oxides and hydroxides together. So they've been ground, right? So as we mentioned, when you're grinding your samples, there can be, processes that are occurring parallel to each other that you cannot avoid. And then the material was annealed in air. So if there was something that could have oxidized, it will, if there's something that can oxidize, it will. So this is a clean pattern. This is a good pattern of this material that was annealed in air. And then we have another pattern that has a slightly different ratio of these metals. But as you can see, there is a phase that's forming here. There is a little peak here. So this is an acceptable pattern. This is also an acceptable pattern. This impurity is very small and can be addressed in comments and explain what it is. So here is the third case of the same material where the impurity peak is very well defined. The intensity is too high, and this is deemed not acceptable in raw data like this. Although this is a known impurity, it is a cobalt oxide that forms. This peak here is too large. However, in the first two cases, data is acceptable. So again, just to recap, the phases should be new and unpublished, of high interest, and what is something that's very useful, is a search link that's provided in the web portal for everyone, for potential grantees, prospective grantees, to see if the phases they proposed have already been published or are in the editorial process. So this is the search that you can use to see if the material that you're interested in, that you're creating, has already been published in the PDF database. As you can see here, it says sorting by quality mark. The quality mark, as most of you know, is how we determine the quality of our data in the Powder Diffraction database. So there are several quality marks going from star to blank, depending on how well the data is defined. So having that in mind, a positive search does not mean that your proposal is discouraged. So if there is a compound that you would like to submit already in a database, this does not have to be discouraging, because first of all, the quality mark could be different. Your data could be more complete than the data we have in the database. Your data may have your data will have raw data, but the data in the database may not have raw data, or same thing with atomic coordinates. So if you are not sure, if you still have some questions, you can always get in contact with Denise Del Casel for guidance on your proposal. She's our Grant-in-Aid coordinator, and her email is posted on the Grant-in-Aid portal and will also be included in this presentation. Once you submit your proposal, it will go to review by the Grant-in-Aid committee, which meets twice a year, in spring, sometime in March, and then again sometime in September usually. What you need to do once you decide to join the Grant-in-Aid program: just register, upload your CV, and a big step is submit your standard reference material that's going to be evaluated to make sure that your instrument is correctly set up. Then you can prepare your proposal. For the first-time grantees, we accept up to 5 patterns to make sure that everything is in order before you can start submitting more patterns per grant cycle. So you can start with 5, and then in the next grant cycle, you can propose more. This is an overview of the Grant-in-Aid portal. Once you start preparing your proposal, this is about your patterns. You want to include different descriptions, how many patterns you're proposing, what your phases are, how are they relevant, and so on. Instrument and techniques, an important step, as I said, in regards to alignment and your instrumental checks. So this is where you can enter all of that data. You can, of course, submit your data for whatever you're working on, which can be organic, inorganic, or duals, like metal organic frameworks, organometallics, or complexes. And I've mentioned earlier, but these will require an additional 2D structure diagrams. That is going to be here in the next, on this slide. I'm showing your compounds proposed, where you can, you can input your name, chemical formula, empirical formula, and so on, and then SMILES, which is required for organics and duals. You can we accept, as you can see, most formats that generally are just exported from ChemSketch. So I want to again thank you for listening. Thank you for being a part of this webinar, and once again would like to invite you to apply for the Grant-in-Aid. We have 2 deadlines per year. One is at the end of January, that's coming up now. The second one is in July. Any questions you may have, please contact Denise Del Casel. She's our Grant-in-Aid coordinator and can help you with anything you may need and want to know. So thanks again, and I hope that this was informative.
Please remember to visit ICDD.com for information on free webinars, educational events, PDF databases, and JADE software.